Alrighty, so come back. Let's go ahead and talk about oh wait. All right. So way back in our Algebra 1 days, this was the standard form of a linear equation because x and y were on the same side and your coefficients were whole values and your leading coefficient was positive. And if you wanted to solve for y to put it into slope-intercept form, you would subtract your x's and divide by the coefficient on y. Everybody remember those days? Weren't those the great days? All right, then we can talk about what is this the equation of? What is b an equation of? What does the graph of that look like? When I have an x squared and I have a y squared, oh, you get a circle, right? X squared plus y squared equals radius squared. So what's the radius of this equation? X squared plus y squared equals radius squared. And the circle's kind of cool. And it's funny because Desmos takes away the joy of figuring out how to represent this doubly. But if you look at, hold on. If you look at your TI, you can graph the circle by making sure that you include your positive and negative. So you could talk about the square root of the opposite of x squared plus 9. And when you go to graph that, we're going to put it on a square graph. Oops, that's not what I want. So we're going to zoom. First, we're going to go standard and fix that. So there's, and you're like, why does it look like an egg? And you're like, well, because you know the TI is not proportional unless you ask for square. So that's the top half of the circle. The bottom half of the circle is going to be the opposite of that same story. So when you want to graph a circle, you have your top half and then you get your bottom half. Anybody know why the TI can't graph the whole circle? Because it's not a function. Yeah, was that unique? Yeah, it's not a function. So when I enter into y is equal to, notice my output is set up in function form. So I can only graph functions. So that's why I have to break the circle into the top and bottom half. But that's okay. I can still solve for y, not a problem. Here we get a little bit harder. We've got some x's and y's all mixed up. I've got to combine some like terms. It would have been great if this was a plus. Then I could have subtracted 1 y squared from each side. And then if I took the square root, you could take the square root of 4. That would have been better. But don't forget your plus and minus. Every time that you draw the square root, you have to think about those two answers. Okay. Anybody have a good time with D? Can you solve for y and D? I have to agree. Nate, you want to tell me why? Like you can pull out a common factor, but it's not gonna help you, especially when you got x's on the other side that don't clean up pretty. So we've got some issues. And we're going to talk about that in our lesson today. Okay, 4 ways we can represent slope. Call them out. Okay, slope, thank you very much. That's nice. Keep going. Change in y compared to change in x. Keep going. Okay, so it's going to be the m in y is equal to mx plus b. This is slope-intercept form. If I want just the slope, it's got to be just the m. Keep going. Thank you. There's our little formula. And if you want to really make a stretch, if you had a hard time getting another one, you could say y1 minus y2, right? Whether you do that. Anybody talk about rise over run? Anybody say the average rate of change? Yeah? Okay. I'll buy all this. How about the derivative? What is the derivative? Okay, we can say it's the slope of the tangent line. Keep going. It's the instantaneous rate of change. I love it. Keep going. dy over dx. I love it. Keep going. So d over dx we're going to talk about in a minute because what I need is a function. Flip over on the back. Each of those d over dx is because I have a function that I'm simplifying. So yeah, that is a notation. I just need a function that has x as the input value. Anybody give me a y prime? Anybody give me an f prime, or for that matter, any letter of the alphabet, right? So, anybody give me the limit definition of a derivative? Anybody give me the limit as h approaches 0 of f of x plus h? Oh, come on. The limit as h approaches 0 of f of x plus h minus f of x all over h. That's the derivative. That one can go up there too. What a great test question. Tell me all the ways that you can represent. So we can talk about the difference between, on your last test, we talked about the difference between your average rate of change and your instantaneous rate of change. Any repeats between the two? Any repeats? So this is as close as we get, the slope versus the slope of the tangent line. This is going to be more specific, right? So these are not the same thing, but you understand, and you can look at how closely they are related. How many of these were you able to get on your own? Please tell me you got this one. Please tell me you got that one. Please tell me you got this one. Right? Isn't he himself? So let's talk about what we're talking about here. This is an expression. I'm asking you, I'm not asking you to solve for the derivative. I'm not giving you the equation e to the x. This is an expression that you're simplifying. In this circumstance, no notation necessary. Do you see the difference? What is the derivative of the sine of x? What is the derivative of the cosine of x? Do you see the relation? Oh, what is the derivative of the natural log? Now, what I really want you to do is seeing the relationship of these to these, because we really still have the natural log of e. Am I putting that on the wrong one? The natural log of e, I want you to look at the difference between these ones as they're given, because I put the natural log of e at the end of this, because this is what I need here, but this goes to 1. The natural log of e is 1. What exponent goes on e to give me e1? So I was right. Times the natural log of e, but this goes to 1. So then if I have a to the x times the natural log of a, you can see this relationship there. If I have 1 over x, when I'm talking about the log, I'm talking about 1 over x, and then I'm talking about this natural log of a being down in there. But then, of course, I don't need that. How'd you do a tangent? Did you remember that one? I was working with a tutor one time, and she said that all of the tangent secants all have two secants and a tangent. It just depends on where they go. Secant, secant, tangent, tangent, secant, secant. Same with cotangent and cosecant. But she said this one was bad. It was negative because it was harder. Cotangent, secant, cotangent, cosecant. There's two of these and one of those. That's how she remembered. That's how she remembered it. Those ones, if we were taking an AP exam, would have to be memorized. We're not taking an AP exam, but when we do the derivatives, having them in our brain makes them easier. So you should, after doing instance after instance, be able to simplify that from your brain. Talk to your partner about which ones you are good with and which ones you need to work on. Go. Today we're talking about implicit functions and implicit differentiation. And it's too big of a word for how much sense it makes. So if you understand why nobody wanted to do this one, and we said no thank you to this one, and how this was even maybe more than what we really felt like doing, then you understand the need for implicit differentiation. So far, all of the equations that we've differentiated have been functions. They've all been f of x is equal to, y is equal to, and off we go. Here's the true story. You know, life is not all pretty equations. So we learn on the pretty ones, but it actually is not very realistic once we get into problem solving. So we need to be able to handle when y is not necessarily already solved for and sitting nice and pretty on the left-hand side of our equation. All right, so here's what we talk about. An implicit function, by definition, is an equation where one of the variables is not explicitly written as a function of the other. So when we talk about an explicit equation, that's where I have y is equal to something, and that's been super fun for us to do all of these weeks leading up to and learning how to differentiate. So they gave you a circle equation. For example, the equation 1 is equal to x squared plus y squared is written in terms of both x and y. And it's funny, back when I was a Algebra 1 teacher, we used to talk about equations that gave you something like this, and our favorite word problems were always, if we charge $4 for the kids coming in and $12 for the adults coming in, and we made $96, give a bunch of combinations of adults and kids that could have come, right? So do you remember those equations where you had two coefficients for the variables? That was that kind of a story. And the kids would always struggle with, well, how come when we put it in the slope-intercept form, why do the number of adults depend on the number of kids? I'm like, well, they don't, but we graph it with this line because there's only one slope-intercept form of the equation. But we can have all those different combinations of adults and kids coming in. So that's actually a more realistic application because we don't necessarily have an independent versus a dependent part of our story if this had to do with the cost of admission of adults and kids, right? One does not depend on the other. In an explicit equation, your output is set up as depending upon that independent variable. So what we're going to talk about is the implicit way that we're going to work on these functions. But first we're going to show you how we could write this implicit function as an explicit function. So we simplified things a little bit from what's in your warm-up, but you got the idea. If I want to solve for y, I'm going to go ahead and I'm going to switch this around and call it y squared plus x squared is equal to 1, if that's okay by you. Then I'm going to say y squared is equal to the opposite of x squared plus 1. And then I'm going to take my square root. And then, of course, don't forget about your plus or minus. So we can rewrite that implicit function as an explicit function. And then when I want to find the derivative, I can go ahead and rewrite this as the opposite of x squared plus 1 all to the 1/2 power. And then if I want to find my derivative, I can go ahead and apply my chain rule. See my outside function to the 1/2 power? The opposite of x squared plus 1 times the derivative of what's inside. Are you with me on this? We okay? This x inside is still negative? Oh, yep, still negative. Thank you. You can go put Smarty up. Okay. Are we good there? Yeah? Okay. So, the idea of the implicit function is instead of solving for y and then taking the derivative, there's another way that we can do this. We can find the derivative by a process called implicit differentiation. But these are the things that you need to understand first about why we're doing what we're doing and the notation of what it is that we're doing. Okay, every time you see a y in your equation, you actually have a function in disguise. And the theory behind this is this. Our x is our independent variable. That's what goes into the function. That y that comes out is always our dependent variable. Meaning without that x, we wouldn't have a y. So when we take the derivative of the y, or the output when the input is x, we are always going to write it as dy dx because we have that derivative of y with respect to x. Now the interesting thing is, if I took the derivative of x, that's going to be the derivative of x with respect to x. And every time I take the derivative of x, I get itself. Derivative of x is equal to itself. Or is equal to 1. Does that make sense? So my dy dx has that inside chain rule kind of idea because I have this and then I need to take the derivative of this with respect to that. And so every time we take the derivative of y, we're going to have to make sure we remember that's the derivative of y with respect to x. If I take the derivative of x, it's the derivative of x with respect to x, and that's equal to 1. So when we take the derivative of our x, that's going to go to 1. Anything times 1 is equal to itself, so we're not going to worry about that. But the derivative of y with respect to x, we're going to have to start paying attention to, because, not to be a spoiler alert, that's what we're solving for. All right, this is how it works. Ready? Let's take this again using implicit differentiation. When I go to differentiate this, what I'm going to do is, instead of solving for y, I'm just going to take the derivative of this whole thing. When I take the derivative, I have the derivative of each individual term. So I can go and say the derivative of 1 is equal to 0 because it's a constant. The derivative of x squared is going to be 2 times x. And if I wanted to take the time to take the derivative of that x with respect to itself, I can. But we're very quickly going to realize that's always equal to 1 and not worth writing out. Okay? Then when I take the derivative of y, I have 2 times y. But I have to remember that this y is that result of or function of x. So I have to take the derivative of this y, which is dy dx. So we notice that this goes to 1 and is not necessary. So 0 is equal to 2x plus 2y times dy dx. If I'm solving for the derivative, this is what I'm solving for, dy dx. We listed it as one of our notations. So that's what I need to now solve to get by itself and isolate. So if I want to get this by itself, I'm going to go ahead and subtract 2x from each side. And then I'm going to divide by 2y. What I end up with is going to be dy dx, which is my derivative. That's what I'm solving for. My 2's cancel out, and I have the opposite of x over my y function. And right now you're like, wait, that's not the same as we got over here. Wait, that's not the same as we got over here. We got this over here, which doesn't look a thing like that. Except for I want you to think about what was our y function. Wasn't this our y function? So can I replace this with y? So now I have y prime, or dy dx, is equal to the opposite of x over y, and that is exactly what I just got. What's really cool about this is we get to leave y as y. I don't have to solve for it and have all that messy stuff to deal with. By taking the derivative of y inside of the equation, I get to keep things simple. And my algebra comes from isolating my dy dx after I take the derivative instead of before. Sound okay? All right, here's our steps. What we're going to do each time is we're going to take the derivative. Each time y is involved, you're going to take the derivative of y of x, giving yourself dy dx. Don't worry about taking the derivative of x, because everybody knows that dx of dx is equal to 1. if you want to go ahead and write yourself a note that dx of dx is equal to 1, so there's no need to do that. Okay, so let's put them all on the back table. Hey guys, can you help out a little bit? All right, ready? Take the derivative of each term individually. So I have 3x squared plus 10y, 8x cubed minus 3. And every time you take the derivative of y, what do you have to remember? dy dx. If you want to think about each of these y's as this y of x, think about that chain rule where you're going to then take the derivative of y in terms of x. All right, so now I have to combine my like terms and get my dy dx's alone. And this is where this thing of factoring comes involved. Because here I have 10y dy dx and 3 dy dx. These are not like terms. So my goal is now to get them on the same side of the equation. 10y dy dx plus 3 dy dx is going to be equal to 8x cubed minus 3x squared. Everybody okay with that algebra? Yeah? So do you see how they both have this common factor of dy dx? This is where the factoring comes into play. Dy dx times 10y plus 3, 8x cubed minus 3x squared. Now this times this, how do I get rid of this? Divide. So my final answer winds up being dy dx is equal to 8x cubed minus 3x squared all over 10y plus 3. So when I have my x and y values, that's what I could plug in to figure out what the slope of the tangent line, the instantaneous rate of change of that value is. So it's more just taking the derivative and seeing how it goes. Ready for number 4? Take the derivative, 9y squared dy dx plus 8x cubed minus dy dx plus 1, 14x plus 5 dy dx. How'd you do on that one? Every time you see a y, you need to make sure that you're remembering to take the derivative of that in terms of x. And we hold on to this y. Now, if you wanted to, you could still put in the dx. You could rewrite this y as a function of x to help you remember. Now I need to get all my dx's on the same side of the equation. 9y squared dy dx is good where he is. This guy's going to go. This guy's going to go. This guy has to come join. So if I subtract 5 dy dx's, and I already have negative 1, do you see how that's minus 6 dy dx's is going to be equal to, I'm sending my 8x cubes to the other side of the equation. I already have a 14x over there. And I'm sending my positive 1 over. You okay with me doing multiple steps at the same time? You keeping track of that, okay? All right, let's get the dy dx out. How do I do it? Say the word factor. Thank you. And you're going to find a pattern of doing things that happens every time. If you've got dy dx's and different powers of your variable, I've got y squared and I've just got 6y's. So I'm always going to end up factoring him out. Always. And then if I factor him out, I'm going to have to then divide. So dy dx, the derivative of y, the slope of the tangent line, at this value with respect to x is going to be equal to negative 8x cubed plus 14x minus 1 all over 9y squared minus 6. And that x and y are your coordinates, input-output, of whatever point you're finding your instantaneous rate of change at. So now we're looking at sine and cosine and e, and you're like, wait, what? No, these ones are always a little simpler, so don't be scared. Don't be scared. Derivative of 4x, 4. Derivative of 1, now, what do we have here? The derivative of the cosine of y squared. Cosine is negative sine, right? This one's missing a notation. I don't like that it doesn't have those parentheses. Cosine of y squared. So it's the opposite of the sine. Of y squared. The derivative of this inside. I feel like this is missing parentheses. It's the cosine of y squared. So it's not the cosine squared. It's the cosine. See the difference between the cosine of y squared? And that's not the cosine squared of y. These two things are the same. That's not that. So the derivative, so this is the cosine of this value, is going to be the derivative of that times what's inside, right? And then the derivative of that 2y dy dx. All right, now I got to solve for dy dx. And this 4 and this 2 can be friendly. So 2 over the opposite of the sine of y squared times y is equal to my derivative. How are we doing? Here's my sine. Derivative of sine is cosine of y divided by 2, right? If you want to call it 1/2 y times the derivative of what's inside. One half dy dx plus the derivative of e to the y is e to the y. Careful. How about that bad boy? So when I factor out this dy dx, what I'm left with inside, and I can pull out this coefficient, and we want to make sure that Kara and I were talking. She was like, I don't understand why y is in the denominator. It's not. It's 1/2 y. So if you need to draw the y, or if you want to put y over 2, for me, if it's easier if you see this coefficient, makes it easier to take the derivative. Because it's 1/2 y times dy dx, right? So if I have 1/2 y and 1/2 y, that winds up when I multiply, oh, no, because that's the cosine. So this 1/2 comes out here. I've taken my dy dx out. So I have 1/2 times the cosine, and you can go ahead and put y over 2 back in that way if you want. And that's going to be plus e to the y, because I factored out my dy dx is equal to 4. So my dy dx is going to be equal to 4 over 1/2 cosine y over 2 plus e to the y. Okay, so on your homework, it asks you to find the derivative of each function. So what we end up going back and reviewing is each of our different situations of how to take the derivative. Now here's the deal. The question is, what do you do with your 90 minutes in class? How much of it is wasted checking your phone, going to the bathroom, and chit-chatting? How much of it is calculus? So you've got 9 minutes left in class, and I'm confident that if I stopped talking, you would all start talking, and some of you would be talking about calculus and knocking the homework out, but not all of you. So we need a higher level of discipline. Doing calculus during calculus. One of the things that drives me crazy is when the first step that everybody has for getting help is, well, I can stay after school. Well, I gotta tell you something. I'm as tired at the end of the day as you are. So the idea of spending more time working, particularly time I don't get paid for, not always my first choice. So when I'm talking to kids that are struggling in class, or I'm talking to parents, my first conversation is, what are they doing with the 90 minutes that they're stuck inside the room? Are they taking full advantage of that time? Are they asking questions? Are they working? Are they on task? Or are they checking their phone, going to the bathroom, chit-chatting, zoning out? So we're all busy people. We got better things to do than wasting our time. So you want to make the most of your time in class, in my opinion. So go ahead, get started.